Hey all, this is Derek, and this is section 7.2, polynomial inequalities. And this section, so we're looking at polynomials again, just like we did in 7.1, but this time we're going to have greater than or less thans rather than equals to. So we'll expect to get solution sets rather than maybe particular solutions if we're just solving set to 0. And we're going to look at two methods for doing that. We're going to use test points, which are perfectly fine, but they're just not the one that I prefer. So I'll do one example of that. And then I think this is easier to, I think polynomials are easier to solve by graphing. So I will show that version. That said, you can use whatever works best for you. And I think rather than going through this big boring box, which I've tried to do a couple of times and I keep cutting it out, I'm just going to go straight into a problem and sort of talk through the methods, and that's going to end up actually covering all this text that I have here. Okay, so first method we're going to look at is using test points. And so the problem with a polynomial with an inequality is that it doesn't quite do, it's not like you can just solve it over like you can with a linear one and one side works and one side doesn't. This could have infinite little chunks of the number line that will be solutions and infinite other chunks that won't. We have to have some sort of systematic way to figure out where our solutions are and where they aren't. So test points is one of those systematic ways. No matter what method we're using, like I said earlier, we're going to start by trying to find our zeros. So that's going to involve factoring this. So we're looking for two numbers that multiply to be -10 and add to be 3. So that will be x plus 5 and x minus 2. And for a second here, I'm just going to write equals 0 because I'm going to actually find the zeros first. So that gives us x equals -5 and x equals 2. So those are the two values that if I plug them in here, that would give me, it would make it come out equals 0. So now what these are my boundaries. So if I kind of think of a number line, I'm just going to call this -5 over here, and I'll call this one 2. If I think of this number line, if I put in -5, this will come out 0. If I put in 2, this will come out 0. So it makes sense that it's doing something else in these other three regions, and that's where I'm going to use test points and figure out, was it positive and then 0 and going negative, or was it negative and then 0 and going positive? Or were they both positive or both negative? We don't know. If you think about what the graph of this would look like, you actually do know, and that's going to be our next method, is graphic, which is, to me, way easier. But here it is with some test points. So I'm going to plug in x equals -6 into this original equation. So that would give me -6 plus 5 and then -6 minus 2. Or -1 times -8, which makes a +8. So what that means is on this region, right here, all of these values are going to be positive. If we look back here, that is actually what I want to happen, right? I want everything, I want all the x's that would make this come out to a positive value, because positives are greater than 0. I don't want the equals, so I would not want to include that part. If I test, I'm just going to pick an easy number between -5 and 2, and an easy number would be 0. So if I test that, I'm going to see what it comes out on this interval. So that would be 0 plus 5, 0 minus 2. 5 times -2 would equal -10. So it's negative on this interval. Negative values are not greater than 0, so this is not going to be a solution. And then I'll pick an easy number over here, like x equals 3. And you can see I'm just picking something convenient from each interval. That would be 3 plus 5. And 3 minus 2, oops, not equals 0, 8 times 1, and that equals 8, and so that is positive. So that means all of this is also a solution. And so that's the idea of test points, is we just figure out where our boundaries are, which is at the zeros, and then we grab one point from each interval and we test it, and if it comes out, in this case, we're working with greater than 0. So if it comes out positive, then that's a solution. If it comes out negative, not a solution. If this had been reversed and this was less than 0, we would have wanted our answer to be the negative region. And then typically in this, we'll give our answer in interval notation. So this goes from -infinity up through -5, not inclusive, union, to infinity. Okay, so the next step will be graphing. And I have graphs here just to sort of draw on something. That said, you do not need to make a good graph, and you'll see why here in just a second. So for this one, we're going to graph this function. And really what we need to do is get the zeros and figure out, is it above or below? So I don't need to look at this like a parabola and get my perfect, here's my vertex and all that good stuff. I need the zeros because that's going to be where those boundaries are happening. So if I just factor this, I would have x plus 4, x minus 1 should multiply to be -4, add to be 3, less than 0. So that is x would equal -4 or x would equal 1. So that's my zeros, -4 and 1. This is an x squared, it's positive even. So just treating it like a polynomial, it's going to be positive even, so it will look like x squared because it is x squared, and it will be opening up. And so that's my graph. I want the areas where when I put in x's, they come out less than 0. And where that's going to happen is right in here, where we are below the axis. So here, when I put in these x's, it's positive. When I put in these x's, I get out positive values. But when I put in those x's, I get negative values. So that region right there, that's going to be between these two x values is where I'm going to get less than 0. And since it has a less than, here I'm just graphing the function, right? So, but here I'm actually dealing with the inequality. So I want to be careful to say -4 to 1 and not include the endpoints on that. Okay, so for this one, same idea. I'm going to graph it and then I'm going to kind of figure out, am I looking for above the axis or below? I like inequalities when it goes x and then less than greater than number. So I'm going to bring everything to this side, and that is going to make this a little bit, So I'm going to add that. That's going to be a 4x squared, and to subtract that will make a -3x, and that is less than or equal to 0. So from here, I'm going to, there's a couple of things I could do. I could factor, well, I need to factor. So I could factor out a -x, and I could leave this sign. Or if I don't like the idea of factoring the negative, I could also multiply both sides by -1. And that will clean up these signs and make it a little bit easier. When I do this, I have to remember to flip the direction of the inequality. And that means I'll be graphing a little bit different function, but it will have the exact same solutions as if you graph this one. I'm just doing this to make the factoring a little bit easier. Again, you could factor out a negative in front and we would get the exact same solution at the end with a little bit different pictures. So definitely more than one way to do this one. And minus make a +3x. And now that's the part of this method that isn't great, is you do have to remember to flip that sign. Versus when you try to factor out the negative, I find people make a lot of sign errors. So I'm not sure which one would go better. I think that's a lot easier to factor. So that's kind of my argument for doing it this way. Looking at that, I'm going to take an x out, and that's going to be x squared minus 4x plus 3 greater than or equal to 0. And then what multiplies to 3 adds to be -4 sounds like x plus, not plus, x minus 1, ignore the big blob, and then x minus 3. And so my zeros are x equals 0, x equals 1, and x equals 3. And so for this, I want to have, let's see, here, here, and here. I could have made this come out a little bit farther. Actually, I'm just going to come down here. And so I'm just going to make myself a little bit bigger picture. And this is kind of what I was saying. The scale really doesn't matter because we just need the above and below. So let me blow that up a little bit to make it easier for you guys to see. This one is okay, so notice I just came up here, which was totally wrong. The function I am actually working on is right here. So even though this started as a negative x cubed, because I did that bit with the -1, I've now turned it into this one. So I have to be careful and graph the thing I said I was going to. So this is going to pass through there, and then come back and go up from there. And from here, we wanted the greater than, so that means we want these positive regions. So we went from here to here, and then from there to infinity, because that's where the graph is, right? above the axis. So that is from, and these are all equal, yep, so that is from 0 to 1, union 3 to infinity. Okay, so this one is already factored, which actually makes it a bit easier. So this is going to be x equals 0, x equals 4, and x equals negative 3. So there's 0, negative 3, and 4. And then that one is cube, so that's going to cross. That one was squared, so that's going to bounce. That one has a cube, and so that is going to cross. And if I add up our powers, we got 3, 6, 7, 8. So if we FOILed all that mess out, it would have been x to the 8th, so it should kind of look like a x squared. So we're going to come in at negative 3, we're going to cross on that one. At 0, we are going to cross again, and it's just to bounce off of the 4. So our graph should look something like that. We again want the greater than, so that's going to be the regions above the axis. So all of these x's give me graph above the axis. These ones do not, those ones do, and these ones do. Here this has this very sneaky little thing. This is a greater than 0, so it does not include the 0, it does not include the 0, and that right there, that's the one that's really easy to mess up. It doesn't include that 0. So this is going to go from negative infinity up through, where was it, negative 3. And then union 0 to 4, union 4 to infinity. And it's really easy to go 0 to infinity and inadvertently include that one extra 0 that can't be there because it can't equal 0. Okay, so for this one we got a negative in front. And I got, let's see, 1, 2, 3, 4 x's. So this would be a negative x to the 4th, and so I would expect this to open down. I have x's at 4, and that's even, so that will bounce. At negative 2, that's an odd, so that will cross, and then at negative 5. And again, odd power, so it crosses. Coming over here, we got 4, negative 2, negative 5. And starting from the bottom, so we're going to come in, we are going to cross on negative 5. On negative 2, I'm going to cross again. And then off of the 4, I'm going to bounce. And so again, here's where I'm not worrying about that y-intercept because it'd be 16 times 10. I think it's a negative 160. So this is going to be way off the graph, which is kind of not what we're worried about. This time we're looking for the x values that make this come out less than 0, right? So if I plug in any of these x's, I'm getting these negative values that would be true. They would be less than 0. Here, it would not be true because I get positive values. This one has an equal, so this time I don't have to be careful with that 0. I can just say everything down here is less than or equal to 0, so I can include all that. So that would be from negative infinity up to negative 5. And then bracket union negative 2 to infinity. And again, nothing special about that point now because of the equals. This is Derek, and I am on the road while I'm making this video, so I'm going to have to talk through the notes rather than do the usual filming myself, filling it out. And if you're in 141, this is a continuation of the inequality section, and if you're in the CoRec, this will be a new video. And for those folks, I'll remind you that we did solving inequalities in the polynomial chapter, and this stuff should look familiar to that. For the people in the 141, that was the first half of this section. So to continue on with this idea of rational inequalities, very similar to what we did with the polynomial ones, in this case, as we just saw, graphing rationals is not that fun, and so the graphing method for solving these probably isn't that good. So I will do one more example here with test points just to kind of remind folks of that method. So this is one totally viable way to get there. Or you can use sign charts, which is the one that I prefer, but whichever one works better for you is a good one for you to do. And I'll do this example 2 different ways again, just to kind of show the methods side by side. So the one thing that is different when we're doing rationals versus polynomial inequalities is that we have to be careful with the denominator. The zeros will occur in the numerator, right? Because that was our x-intercepts. But remember, we had asymptotes at these points in the denominator. So x can equal -3. It just makes it come out 0 over something equals 0. But x can't equal the 5, but there can still be a sign change there. So what I do, and I'll show you over on my sign, or I guess this is more of a number line for test points. So -3 and 5, those are my zeros, so to speak. But I'm going to label the 5 from the denominator with a little u, and that's just to remind myself that it's undefined, and that I can never include that point because it would give me division by 0 and it's not in the domain. And then the numerator, though, I do want to include that one because this does have an equals. If it didn't have an equals, it's totally easier. Then everything is just open dot and parenthesis. But you do have to be careful with these when there is an equals for that denominator. Okay, so for test points, the intervals I want to look at are from -3 to infinity, between -3 and 5, and then from 5 to infinity. So I picked the next integer over, -4, and I put that into our original equation here, and that got me 1/9, which is a positive value. And we don't actually care it's 1/9. Once we can see it's coming up positive, that's really what we need to know is positive or negative. Between -3 and 5, I picked 0 because that seemed easy. That came up a negative value, so I'll mark this interval right here as a negative. And then I probably put in 6, yep, and that came out to 9, which is a positive value. And so in this case, we want this stuff to come up greater than 0. Numbers that are positive are greater than 0, remember? Numbers that are negative would be less than 0. So when we're solving a greater than, we're looking for the positive values because that's what makes the statement true. So everything from -infinity up through -3, and then we're including that -3 because it's in the numerator. And we use our union to bridge the gap between the intervals. And here, remember, this is our undefined because we can't have it be 5 because that would make it's not in the domain, it's where the asymptote was. So we use a parenthesis there and then 5 to infinity. So that was with test points. And then here's the exact same problem but with sign chart. So I just set up to remind you how these go, I did x plus 3 and x minus 5. Here is the same exact number line right here. And then what I would have a 0 at -3 because that makes this one 0. And I'll have that little u there to remind myself that that would make this one undefined and I don't want to include that point. And 5 is what makes that one 0. So then if I'm to the left of 0, the 0, it's going to be negative like we saw before. You can also do a little test point if it helps, just to kind of settle your mind. If I put -4 in here, that is negative, and then it goes through 0, and everything after that's going to be positive. You can try something, put in 0, it's positive. But this is just, it's a line that's increasing, so once you pass through 0, it's going to go -0, and then positive. If it's something like that with that positive 1x, because that's going to be increasing left to right. See the same thing here. We could put in test points, or once we kind of realize, hey, it's going to be negative on the left of the 0 and positive on the right because it's a line that's always increasing, you can just go negative, negative, positive without having to think too hard about it. And then here we look and we go, 2 negatives make a positive, mixed signs make a negative, 2 positives make a positive. And then from that we get the exact same interval we did up here, and again, being careful to not include that 5 because of the denominator. Let's see, so the next example is going to be something pretty similar. This one's going to be a less than or equals 2, so now when we go to look for answer, this time we're going to want the negative values because those are the ones that are going to come in under 0. As is my preference, I did these as sign charts, but if you are happier with the test point method, by all means use that. For me, I'm a little more visual, so this works pretty well, and I'm good at dorking arithmetic, so this isn't my favorite method. So for me, I did a sign chart, and I just set up my x plus 1, and that one's 0 would be at -1, so we'll see. I put my 0 right there. X plus 3 from the denominator, so that one's 0, which is undefined, would be at -3. And then x minus 4 would have a 0 at 4, and then also undefined. A note on this, it's really easy to like go -1, 3, 4. or -1, -3, 4, to do them in the order that you listed them. And careful to get the number line in the right order. It sounds like a dumb thing, and people just, they do it all the time where they're like, okay, -1, -3, and 4. And you got to be careful to get it in the order it goes. I usually fill this in first so that I'm thinking, and then I match my stuff up. So these are all x plus, these are all positive x's. So again, these are all going to be lines. If you think about what that graph would look like, it would be, if I had a graph, it would be increasing, and x would be the y-intercept would be at 1, and be just going over 1, up 1, over 1, up 1. So its x-intercept would be at -1, and so everything to the left of -1 would be negative. Everything to the right of -1 will be positive, which is exactly what we see here. If you don't love that explanation, you can also go with, as long as you got positive x's and no squareds, it's going to be negative on the left of the 0 and positive on the right. So here you can see I'm just going negative, negative, and then 0, positive, positive. For this one, here's our undefined point. So it's going to be negative to the left of the 0 and positive to the right of the 0. And for this one, here's our 0 over here, and we're going to be negative to the left of the 0 and positive to the right of the 0. So then after that, we are going to, we have 3 negatives, so multiplying those together would be negative because we have an odd number of negatives. Right here we have 2 negatives and a positive, so 2 negatives make positive. We have a negative, so 1 negative makes negative, and here 3 positives make positive. And remember, back here we are looking for where this is less than 0, and so in that case we have this region over here was negative, so that's going to be negative infinity to -3 union, and we have an open dot. Remember, this one was our 0 from our numerator, and this was undefined again, and then so there's our -1 to 4. And again, just be really careful with those endpoints. And then for this last one, so we have this numerator that needs factoring, and anytime, remember with these, that there's something that has to be, that something can factor, we should factor it. So we get x plus 3, x minus 3. So there you can see, if you remember back to the section on rational equations, this would reduce out and we'd end up with a hole in the graph. And that's, again, getting kind of dicey to see as we're kind of doing this with sign charts or here. So let me show you a couple of ways to look at it. I could not reduce and just see what happens because I know this is right. So let's see what that does, and then I'll show it with reducing and then kind of explain what happened. So without reducing, I'd have x plus 3, x minus 3, x plus 3. So there they are, x plus 3, x minus 3, x plus 3. So I'm showing both of those factors in there. And for the numerator, x plus 3, I have a 0. But then for the denominator one, it's undefined because of the division by 0. And then our other factor right here is this 0 at 3. So same old, if it's going to be negative on the left of the 0, positive on the right, as long as these are all positive x's, that will always be true. And so this is just filling in the same, and then negative, there's our 0, positive, positive. And if you look at our two factors that were the same, negative times negative would have come up positive. Positive times positive is positive. Positive times positive is positive. So the only thing that this is contributing by having those factors there is reminding me that this thing is undefined at -3. And we'll see that in this next example as well. And so 3 negatives make negative, 1 negative makes negative, 3 positives makes positive. And notice we get kind of like, we're used to the signs maybe flipping back and forth at this point. This one didn't, because we got this kind of funky double factor top and bottom. But what we're looking for is the less than or equal to zeros. So that's going to be all these negative regions. So it's everything from 3 out to the negative infinity except that -3 there. And that's the good part about not reducing is it makes you kind of deal with the fact that you have a denominator that you have to make sure that you exclude from your answer. And it's really easy to forget that. Or if I were to reduce, say I canceled that out, what I'd have to do is just write down or tell myself somehow, hey, when you do this, that's all fine, but x can't be -3. And as long as you make that notation, and that's going to be our restriction, I can go ahead and just do this very simple little x minus 3 is less than or equal to 0. Bring that 3 over. There's x is less than or equal to 3. That's just what we got up here. And I have to remember that, hey, because I did that reduction, that it can't be -3 for the interval notation on that. we are going to have from negative infinity up to -3, and then because that's an open dot, we have to do this kind of funky -3 parenthesis union parenthesis to exclude -3, and then on up to +3, and then that one was a bracket again because that came from the numerator. We're being careful, that came from the numerator here, and here we're being careful to exclude that value because of the division by 0.